Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we'll be looking at the work of Castine Bernardy, a PhD candidate at the University of New Hampshire, United States. Bernardy's dissertation focuses on ultraviolet or UV surface disinfection under the supervision of Dr. James Malley, a UV disinfection expert, editor-in-chief of UV Solutions Quarterly and founding president of the International Ultraviolet Association. The wavelengths of visible light cover 400 to about 750 nanometers. Germicidal UV encompasses wavelengths between 200 and 320 nm, with the most common wavelength utilized by the UV industry at 254 nm, as it is the most energy efficient at commercially available wavelength. This wavelength damages viral and bacterial DNA or RNA. This makes the bacteria or virus unable to reproduce, rendering it inactivated. Because of the damage it causes to DNA, extensive exposure to human skin and eyes is not advised. Bernardy's research was catalyzed by the onset of the COVID-19 pandemic and the shortage of FFRs, filtering facepiece respirators, also known as face masks. UV surface disinfection has not been well studied for effectiveness and is not regulated. Prior to the COVID-19 pandemic, UV surface disinfection received little attention. Currently, the most common use of UV disinfection technologies is for water disinfection applications. On a smaller scale, devices designed to sterilize household items such as mobile phones with UV light gained a boost in popularity during the pandemic. However, due to poor design and lack of regulations, these devices may create a false sense of security for the user, as they are likely not to provide the level of disinfection suggested by their marketing. The goal of Bernardy's work is to determine if UV is a practical technology for FFR disinfection and add to the body of knowledge needed to create regulations for UV surface disinfection devices. UV disinfection is used for drinking water, wastewater, and water reuse applications globally. Regulations such as the US EPA Disinfection Guidance Manual, Austrian ONORM, and German DVGW exist to ensure that these systems deliver an adequate UV dose to the water column to inactivate target virus and bacteria. The COVID-19 pandemic sparked significant interest in extending the current use of UV technologies from water to surface disinfection, despite significant gaps in understanding its efficacy and in its regulation. Yet, the US market for UV surface disinfection devices was projected to increase by $4.4 billion from 2021 to 2026. Without proper regulations, UV device design may lack consideration of key factors such as user safety, appropriate viruses, bacteria used for testing, optical design, and surface characteristics such as porosity, contact angle, and surface roughness. Porosity is measured as a percent and refers to the void spaces in a material. Contact angle is a measure of the wettability of a surface, specifically if it attracts or absorbs water. Finally, surface roughness measures the smoothness or micro-irregularities of a surface. UV surface disinfection research began in the Malley laboratory upon inquiries from medical professionals in the US regarding UV disinfection of filtering facepiece respirators, or FFRs for short. The globe was facing an FFR shortage, and hospital staff were in search of a method to disinfect their FFRs safely and effectively for reuse. These professionals had access to a UV disinfection machine designed to disinfect CPAP machines. The device was not intended to be utilized to disinfect FFRs, although during this crisis time, medical professionals needed to use the equipment they had access to. Bernardy's research tested the efficacy of UV disinfection on 4 FFR types. 2 KN95 and 2 N95 FFR models were selected for this work. The experiments utilize E. coli bacteria and MS2 bacteriophage viruses as the microorganisms for this research. The team tested UV doses ranging from 0 to 2,000 millijoule centimeter squared for each respirator. The industry measures UV dose in millijoules centimetre squared, which is a function of the disinfecting power from the UV lamp, aka UV irradiance, multiplied by exposure time. UV254 was used for all the experiments conducted in Bernardy's laboratory, the industry standard for sterilization. The team had many unexpected but important findings from these studies. The best results, or highest levels of inactivation, were observed with the KN95 purism respirators. This peak inactivation was observed at 1500 millijoules centimetre squared for both E. coli and MS2 bacteriophage, achieving almost 99.9% or 3 log inactivation for both surrogates. The UV doses utilized for this work were significantly higher than doses commonly used for water disinfection. To put it into perspective, a typical UV dose for water disinfection is 40 to 50 millijoules centimetre squared. The porosity of the FFRs created something referred to in the UV industry as the canyon wall effect. Virus and bacterium are incredibly small, with typical diameters in the nanometer and micrometer scales, respectively. Therefore, the pores of the respirators can act as a shield for the virus or bacteria by blocking the UV wavelengths. Additionally, these experiments proved to be challenging due to the variation in materials, porosity and structure of the 4 respirators. The intended function of the FFRs is to trap bacterial and viral particles within the respirator fibers. After the FFRs received their respective dose, they were rinsed with a sterile phosphate buffer solution and analyzed to determine the remaining infective surrogates. These experiments were also conducted for the control points, 0 millijoules centimetre squared, to quantify viral bacterial recovery without exposure to UV. The team found that the recovery varied significantly between FFR types, with significant variation also observed within FFR types. The differences in material type, porosity and number of layers influence the electrostatic interactions governing viral and bacterial retention within the FFRs. Finally, the most important finding from these studies suggested that exposure to high UV doses caused degradation of the FFR fibers. It is known from the literature that UV wavelengths degrade polymers. Bernardy's work demonstrated that UV doses of 2000 millijoules centimetre squared and above cause respirator degradation. At these high UV doses, the recovery of the MS2 bacteriophage and the E. coli increased when compared to the recovery at 1500 millijoules centimetre squared. The data suggests that the high UV dose degraded the fibers responsible for the electrostatic interactions, therefore allowing viable virus and bacteria to pass through the respirator. At lower doses, these bacterial and viral particles were trapped within the layers and fibers of the FFRs. Although when fibers begin to degrade, they pass through when rinsed with the sterile phosphate buffer solution. There have been many studies reporting on the degradation of FFRs when exposed to UV wavelengths for disinfection purposes. These studies have used a variety of methods to evaluate FFR degradation, such as tensile strength tests, flow penetration of abiotic particles, and have concluded that UV doses of 2000 millijoules centimetre squared do not cause degradation of FFR materials. This work is specifically important to the industry because it was the first study to use virus and bacteria to quantify the effects of FFR degradation. While signs of degradation may not be visually apparent, the work proved that damage occurred to the fibers responsible for the electrostatic interactions within the FFRs. This research demonstrates the importance of using virus or bacteria to test for the degradation of FFRs, which was published by the American Society of Microbiology in the Applied and Environmental Microbiology Journal, which can be found in the show notes below, as well as on Bernardy's LinkedIn page. The research team was inspired by these results and is currently researching the impact of surface characteristics of UV disinfection of aluminium, ceramic, formica laminate, PTFE, known as Teflon, and stainless steel. The team is looking into the efficacy of an alternative wavelength and varying environmental conditions. When published, this work will also be available on Bernardy's LinkedIn page. That's all for this episode. Thanks for listening, and be sure to stay subscribed to ResearchPod for more of the latest science. See you again soon.